Alright, let's do a video on designing a simple OPAMP in Cadence using the GM over ID technique. So this is for 45 nanometer. I've just chose the first NMOS transistor that's there and set the length to 10 times the minimum length and then the width to 10 times that. And we are going to diode connect it and sweep DC. And if you want to see that, if you've forgotten how, you just under tests, right, you can double click on tests and it should come up. Or if I'm on tests, options, create test. Alright, so we're just going to start in DC, so we're going to choose a DC analysis, and it's going to be a component parameter, select it, which is that DC value. We're going to sweep its DC. You can see that we can do other things, right? And we're going to go from 0.1 to 1 volt. 0.1, so at least some current flows. Apply here, and we should just be able to run because I've already clicked plot on the for the current. And to do that, you just would click on the on this, and then all four things will pop up, and then you can delete the currents. But when you're creating your test, plot on schematic, just click there. This isn't meant to be a complete review of how to use Cadence. Okay. So it's running. And that should be the current through the NMOS drain. We just click on that. And there we go. Now let's calculate GM. So we go to Tools, Calculator. Actually click on this, and then now that's the actual signal in question. So we want to take the derivative of that. So just type in deriv, open and close, parentheses, and then GM over ID is just that. And there's the current. Okay, you can press enter. Tools plot, and there's our GM over ID. Let's see, can I get that on a log axis? Okay, there we go. So that's on a log axis, and that's the current. Now we want this, actually we want this DC here to not be logarithmic. So we just double left click on that and it should pop up. Or right click on it, I guess. Axis properties. I'm just going to let that go. Now I want to do Y versus Y, and this is the current, and I'm going to want that on the x-axis. All right, and I should. Not quite sure why that isn't popping up. to let me do. There we go. Okay, that's logarithmic. That's not logarithmic. All right. Now, I'd like that on a log axis. All right. So you can kind of get that medium inversion point. And so if I was looking for that and I wanted like 100, let's make it more full inversion, and I pull off a point like 100 microamps. That's there, that's better. I was plotting the current, I believe. So let's get us to 100 microamps. And that gives us a GM over ID of 7, right? And then, but what's the VG of 100 microamps? Or the VGS, excuse me, is I just bring it down here and it's like 649, right? So that gives me my bias points to select everything. Now, if you change anything here, you have to rerun it, replot it, and then it doesn't automatically update the these. You have to kind of do it each time, what I just went through. I'm going to get rid of that. Now if you want to see so this is the now I want the output resistance of this, so the bias point here I'm going to use 6.59 millivolts, and then I'll just sweep this, right? And it's the same thing, you just have to choose a DC analysis, select that component, right? Run it, plot it, okay? That's the saturation. 1 over that slope is the output resistance, and so you click on that current, that signal, go to calculator. All right, now this is going to be 1 divided by the derivative of that. And so this is your output resistance, that, you know, changing quite a bit. All right. So in our area, you know, as we're sweeping above, right, so we're hopefully in saturation. You know, 32 kilo, okay? So you can use all that to find what the gain should be. And you can do that. You can find the output resistances for the PMOSs as well. Now, this would be a ugly but simple op-amp where all these all these NMOSs are the same weight, length, and width. I've used the 4-terminal devices. My power supplies are plus or minus 1 volt. I have VN effectively connected to 0, and I'm going to sweep VP. So again, in the tests, right, if I choose that, I'm sweeping. The thing is, I know that I'm around 0 where it's going to be interesting. So I've kind of zoomed in on it and taken a lot of steps. All right. Now, I run that. And here's my V in versus V out. And if I take the derivative of that, sorry, we got construction in my house. Just click on that signal. Calculator. And that we just want the derivative. We see the maximum point is almost 500 gain, and it's happening, within 500 microamps of 0, 5 microvolts of 0. You can zoom in and see, 805 microvolts minus. So that's our offset, which is pretty much controlled by the lengths and widths. For what this design is I've got a width of 1 micron, length of 450 nanometers. The width here is 4.5 microns. Length is still 450 nanometers. And here it's an effective total 36 micron width and effective 450 micron width. I had to play with those to get that, to get the output voltage, the offset voltage close to 0. But that should be enough to get you going, just at least on the DC. The next step would be to do an AC analysis and determine that feedback capacitor and resistor, so that the op amp is stable.